Hi guys, and welcome to the Genome2D DevCast number 3. So what are we going to talk about today? As many of you know, I'm quite often hired to optimize different GPU based engines by various companies, and they don't necessarily need to work with Genome2D. They have their own in-house engines and stuff like that. So recently I was hired to optimize this engine, and it wasn't about speed. It was they had enough performance. There wasn't a problem with the rendering performance. What they did have a problem with was that they couldn't put all their assets into GPU memory. So I was given this task, and first what I saw is that let me show you an example of a game. For example, Tiny T. Tiny T, if many of you know this game, it's using ActionScript, and even though it's not using Flash or Air, it's using Scaleform. So what I saw in this project, it wasn't Tiny T, it was a different project. I can't talk about the specifics of the projects or the engine, is that they used all these simple textures. It wasn't a very complicated texture color-wise or some kind of pattern. So first thing I told them is like, guys, we need to use vectors because it would be more feasible to pack to a smaller GPU footprint than for example this tree. I mean, when a vector, it would be really small in GPU memory, and the bitmap is will be quite huge. But they declined this this approach. I don't know why exactly. Probably asset management or some kind of program. I don't know really. So I thought again about how we can optimize this, and what I came up with, it's not necessarily new thing, and we are going to talk about it today, and that's texture packing to color channels. And I'm going to implement it in Genome2D through a custom renderer, so you can try it out if you want to. Many of you are probably familiar with this, especially if you packed, for example, grayscale stuff, grayscale textures. So I prepared this texture. I took the font from the Genome2D examples, and as you can see, it's a grayscale texture. It's 256 to 256 texture. And if we have a grayscale texture, it's easy to pack because we can simply take this and put it to a red channel or a green channel or a blue channel or alpha channel. Doesn't matter, and then just render that channel without the others, or more specifically, like take that channel and put it to all the others and render that out. And we need to dismiss the other channels because all in the other channels will be different textures. But what we needed in our case, in this project case, is that the textures weren't grayscale. They were color, for example, like the Tiny T, they had a specific color. So I updated this approach of texture packing to color channels, and with a palette lookup. So what I did first is I took this texture and iterated it. Let me show you. And I went so we have this atlas with all the textures, subtextures, that I went through all the textures and created the bitmaps for all these textures, and created an index bitmaps. So I went through the textures and through all of them, all of their pixels, got the color from the pixel, and checked if their color is already in my palette for that bitmap, and if it wasn't there, I put it there, and to the same place of the pixel, I wrote the index to the palette. So for example, let's go over the image here. Let's say I'm at this pixel and I'll check that there is a color of 255, or let's say white color 2055, 255, 255, 255. So there is no such color in our palette. So I take it, put it into the palette at the first place, for example, if it's the first pixel, and then I write at the same pixel where I took it the number 0, because it's the first index to the palette, and like this. So instead of actual texture, I will create the index texture. So the pixels in the texture I'm creating do not tell anything about the color. It tells that the index to the palette for the color. And next, so we will create, I don't know how many textures are there, for example like 50, I'm not sure. We will create 50 textures, 50 different bitmaps with the indexing to the palette, and at the same time we will push this palette. It will be just one line for one texture, and since the maximum color, in our case, we can, in different packing, we can use 2 channels, for example, for color packing. Let's say we are going to use 256 colors as our palette. So we will create a palette bitmap which will save the palettes. For the first texture will be the first line with 256 colors or less, because there is nothing telling that this bitmap is using the 256 palette. It may use, for example, just 10 colors. It doesn't matter. So the first line is the first texture palette, second line and stuff like that will be the second. So we will have all these index textures plus the palette texture. And now we take the index textures and repack them. We could use the same atlas, for example, and just put the indexes there, but there would be no optimization. We need to take the textures and put them to four times less of the size of atlas. So if we have a 256 times 256 texture, now we can, since we are going to use 4 color channels to pack these textures, we can use 128 by 128 texture atlas, because we can pack 4 times the amount of textures in the 4 channels. So we'll take all these textures, create the, in my case, since as you could see, even though it's a 256 by 256, because this is exported by Litera, and I don't know why Litera couldn't pack this to 256 and 128, but doesn't matter. In my case, I'm able to pack all these into a texture of the size 128 by 64. So it will be 8 times smaller than the initial atlas. 8 times smaller. So I will save a lot of memory. Now, how it works, it's pretty simple. I'm using internal max-rect packer algorithms inside Genome2D, and I create 4 of them because I know there will be 4 of them, and just put all the bitmaps as I can to each packer. So I create the first packer, I put as much as I can to them, and remove them from the data list. Then I am going through the second packer, and again I put as much as I can to it and remove it, and so like that. It's like I am filling it up with the bitmaps till there is nothing more. So I will end up with 4 different max-rect packers. And now, since I have the textures packed into 4 different subtextures or textures 128 by 64. I need to draw them out. Some of you may think why we just didn't split this up 4 times, because we can do that because we need for the whole subtexture, for example this C here, we need it in a single color channel. So if we split it up just like this to 4 times and put it on top of each other, we could end up with splitted subtextures, which isn't going to work, because part of the E here would be in a red channel and part of it would be in blue channel, and it wouldn't work. So now that we packed it correctly into 4 different packers, we are going to draw it into a single bitmap. Or I'm going to use byte array in my example, because bitmaps in Flash use pre-multiplied alpha, and we are using just raw data. Even we are using even alpha channel to pack the textures. So if you use the bitmap data and set pixels 32 and stuff like that, it wouldn't work, because it would mess up your pixels due to the pre-multiplied alpha stuff. So I create the byte array, and now go over all the subtextures, all the textures in the packers, and just write it into it at the correct position. So this Y here tells me which packer I am in. So first packer, or the 0 packer, will be the alpha channel, I think, and that will be, because byte array is ARGB, it's not RGBA. So, but it doesn't matter. If you try it out, you would see which channel is used for what. But there is some mix-up, because, for example, in using the bitmap data, it's RGBA, but using the byte array for the texture upload, it's ARGB. No, the other way around. It's ARGBA. In the bitmap data, and for the texture upload is the RGBA. It's just sometimes it's the alpha channel first and sometimes it's last. It doesn't matter, because we are going to use all the channels for the same thing. So it doesn't matter where the alpha is, because we're just using like 4 uniform channels to peg our textures. So again, I'm using the byte array and the position to the correct pixel, and this is to tell it to correct channel. So it's the uwind at this position, and this tells us it's alpha, it's red, it's green or blue, and I just write the index here, where the index is the get pixel I got. So it's the index I am writing here. So I got the lookup here, where I separated the palette and set the textures to just refer to indexes into the palette, and here I'm just putting it into a byte array, because I just repacked it to correct format. I can show you, because at the same time I'm going to publish a blog post about this to summarize it, and I have this example here. This is how the texture, the 128 by 64 result will look alike. This is not exactly how it will look alike, because this is without the alpha channel. You will see in the example I run later, is that if we are using the alpha channel for the packing as well, there will be almost nothing visible, because the the palette is most of the fonts or the glyphs use just very small amount of colors, and the palette is of like 0, 1, 2, 3, and the alpha channel is therefore very low, so there will be almost nothing visible if I show you the exact texture that will be the output. This is just the texture using the same approach, but packing just to red, green and blue channel. So these are the indexes all over themselves, and don't worry, we will use the pixel shader to extract it and render it correctly. So now that we have this texture in our byte array, we are using Genome2D to upload it. So we will upload the byte array to Genome2D to create the Genome2D texture, and then so we are there is no factory method to create such a texture, such a specific texture I'm using here. So I'm using direct approach to create a Genome2D texture atlas. So I'm using a byte array, and then I'm going all over the packers and adding them as subtextures to refer to their correct regions. Keep in mind that many subtextures here will intersect. There may be like 5 different textures intersecting their regions. This is normal. This is okay, because even though they are intersecting inside the UV region, each of them are in a separate color channel. So the output is actually not intersecting. Now I'm going to invalidate native texture to upload it to the GPU. And this is just my something fancy to show it off. And this is I'm going to get all the subtextures from the atlas. I'm going to render because we need to create the palette as well. This is the color data. This is the palette I told you about before, where I'm saving the colors, the actual colors. So the atlas just contains indexes in the different color channels, but there are not the actual colors of our original texture. Just the palette refers to the colors. So I'm creating the simple texture for the colors, to the palette texture as well, and I will render it to show you how it looks again. And now, as I told you, I'm using a simple renderer. I updated the custom Genome2D renderer, which I talked about in previous Genome2D DevCast, and I updated simple batching, so don't worry. So this is most of this code, almost like 99% of this code is the Genome2D batching. I just updated its vertex and fragment shader, and of course I updated that we need to upload some more info to the GPU to process and separate the color channels and process it correctly. So what we need here, and we are going to upload as well, is I'm using vertices, vectors, not byte FASMEM. So what we need here, as you can see, this is not optimized enough because I'm using just 4 of them and 3 of them are unused. 4 of the 3 of the registers. This it's ambiguously named, but this is the index to the palette. So each texture, as I told you here, each texture is a single line in the palette image. Okay, let me run this first, so you see how it works. This is the original atlas. This is the packed atlas, the top left. As you can see, since, as I said, we are packing to the alpha channel as well, there is almost nothing visible, something here, up here. And this is the color palette, since because we are using grayscale. This could be any colors, but if you tried to use grayscale like this, it's a waste of texture lookup, because you don't need a texture palette for grayscale. You could just put the grayscale there and without the palette, but it's a common technique. So if you want to know more about that, you can ask and I will tell you, and I even refer to it in the blog post, but I'm not going to talk about that. So this is the palette where all our colors are, and each of these textures, for this texture is the first line in the palette, this one is the second line, and like that. So I need to tell the custom renderer, the Genome2D custom renderer, that this texture or this texture or any of the texture refers to this line, because there is no connection between it from the Genome2D standpoint. So I need to upload to the GPU constant or buffer or any batching you are using. You can use this with the buffer batching. You don't need to use constant batching. Anyway, so I need to tell that this A texture uses, for example, the palette at the line 28. Let's say it like that. And another thing I need to tell it is the color mask, and this is used to separate the correct channel which is using. So I need to tell again Genome2D that this texture is compressed into the, let's say, blue channel. I don't know if it is, but let's say that T is in a blue channel. So this color mask, and it's using four-dimensional vector. I could optimize it from this standpoint, but as you can see, using a four-dimensional vector, we can just use a single fragment shader operation to mask it. Anyway, so this is the color mask, and this will be like 1 0 0 0 or 0 1 0 0. It will just be 1 for the correct channel the texture is using, where it is specced. So if it's specced in the blue channel, it's 0 0 1 0. So now that we have this, to the texture, the palette index, and the color mask, we will just send it to the fragment shader. So we are sending it to the varying 2 and varying 3 registers. And now, very simple fragment shader magic. We will sample the atlas, the texture, that's the packed texture. Nothing changes here, it's the same as if we had correct atlas or anything like that. But we are not going to use this for output, because it would output the mess, the indexes in the color channels. So what we are going to do is dot product it, and this is why I used 4 registers. Dot product it with the color mask. So it will remove all the channels that are not correct. So if the color mask is just for the red channel, so it's 1 0 0 0, it will remove all the unnecessary stuff that is in the green channel, because we have something in the green channel, but it's a different texture. It's for a different texture. We don't need you to use it for this output, and then the blue channel and in the alpha channel. So this will just output the correct index value, the palette index value, for the red channel, which is specified by the color mask. And now that's for our X in the UV coordinates, because this is the index in the color palette for that texture. And secondly, we need to put in the UV, in the V parameter, our texture index in the palette, which is the line. So first, which we color masked, is the index from the texture, which is the column in the palette, and second is our index in the palette for the texture. Since each texture has its own line, we put it in. Now we can, since we have a correct UV coordinates, we can just texture sample the palette. So we already know which color we will need, and we sample it from the palette and output it. And that's how it works. So this is output from the packed 128 by 64 atlas. And as you can see, maybe you don't, because this recording slows it down, but it's running at 60 FPS and it's a couple of thousand sprites. Doesn't matter. on the low-end mobiles it would, but again in their project they didn't have the problem, and in most high-end mobiles you will probably run into memory problems instead of performance problems, because this pixel shader isn't that heavy. So if you can spare some performance and need to pack textures, and your textures are simple enough to be able to pack into a single color channel, or you can even use 2 color channels, but then it's like I'm not sure, because I will create the atlas in half, but I will need an additional texture, which is a palette. You can actually use a 3 color channels packing and the fourth channel for a definition of the index, or to specify the packing in the switch. This is quite a complex, but there are a lot of different approaches that can be modified from this, that it's pretty awesome. They used it and they were able like 4 times the amount of assets to put into memory, so why not? And you can also combine it. So for example, some assets are heavy, color heavy, so you will just use a different atlas without this pixel shader. Of course you can't batch it together, but batching is not always needed in such extremes. So if you know what you are doing and combine it correctly, there is no downside to it. And of course, as I said, you can use just the grayscale packing. So you would go about it very similarly to this. You will not save indices. This is not needed at all to extract the palette and stuff like that. You would just take the textures, repack them 4 times, and just output the correct color information into the packed atlas, and you will not need the palette index, but you will need the color mask. So you would just do this and output it. You would just discard all the incorrect channels which are not needed, and then just output the correct into all the 4 channels on the screen. And you would, in this case, in my case, because I'm using grayscale, you would end up with the same thing, but this can be applied to any colors. And of course this is great because, as you can see, and most of you already spotted, this doesn't mean that your game is 256 colors, because you are limited to 256 colors per asset. So this single texture can have 256 colors, but this the second texture can have completely different 256 colors, and so on, because they don't need to share them at all. If you are sure, for example, that your assets use, for example, just 16 colors, 16 different colors, and so you can just allocate your texture or your palette texture to 16 width, obviously, and stuff like that. So okay, guys, that's all for today. If you have any questions, feel free to ask. I'm not going to push the custom renderer yet on the GitHub, since it's not official and it's not clean enough. If you want to try it out, you can ask me. I will give it to you on our Genome2D forum. And I'm also going to publish the blogspot which talks about it in a more agnostic way. No Genome2D used in this. It's just how I approach it. Because obviously the engine I was optimizing, it wasn't ActionScript and wasn't Genome2D. So thank you for watching, and I hope you liked it, and thank you.